All right. Yeah. Thank you for the nice introduction. Yeah. As he introduced, my name is Jung Park, and today I'm very happy to talk about my work and give a talk about synthesizing reality for 3D media. So the goal of this talk is to introduce the recent progresses in the field of 3D reconstruction and synthesis through the lens of my past works. And these technologies that I'm going to introduce could be applied for many applications, such as visual interactive new media or other industrial or cultural applications. So this image that you're seeing is a prehistoric wall painting on a cave wall that is drawn in 33,000 BC. These wall paintings were drawn by the cavemen with this state-of-the-art technology and rare materials at the time. So this shows that humans have natural and strong desire to record and share the experiences in various forms. With the advancement of modern camera technology, now we can take 2D snapshot of the world with just the tap of our fingers. We can also add time dimension, which makes it videos. And videos allow us to record the changes and movements of the world, such as these cute moments of your pets. Although paintings, photographs, and videos are all great media for a lot of different purposes, they have the limitation of being static snapshots of the world. And by that, I mean, we cannot change the viewpoints of already recorded video and watch the scene from a different perspective. Or we can't put our hands into the video and pet the cat. So I really don't think that we as a human being have reached our maximum potential of reconstructing the reality. And we will see some dramatic changes in how we record and consume the media in our lifetime. So I think the next generation media will allow us to do something that's beyond what's recorded in the video. So a good example of that would be virtual tourism, where you can virtually walk around in a scene such as this Louvre Museum, and everything would look realistic in everywhere you look at. And I expect that we can take a step further from there, and the new media would allow us to interact with the scene. For example, picking up some object in the scene or talking to the people in the scene. And in order to enable all this cool stuff for the 3D media, I think the first step would be to understand the physics behind how pixels are generated. For example, we can study how camera is modeled or how the surface geometry is in the scene, and even think about how surface reflects the lighting, and so on. However, there are some things that cannot be achieved with this pure physical reasoning. For example, we cannot possibly capture a scene from all viewpoints. And there are moving objects as well that will hinder us from capturing all different viewpoints. And therefore, we need to learn from existing knowledge and data to complete the unobserved regions, or to simulate how an entity might behave or move. For example, how would people in this scene would appear in different perspectives, or how would they walk, or how would they speak to each other? To enable this 3D learning, we need to devise a good 3D representations that are suitable for learning and synthesizing from 3D data. And finally, we can use these physical understandings of the world and the prior knowledge learned from data to achieve 3D synthesis in various forms. An example of that is the famous 3D reconstruction, which tries to synthesize novel views of a captured scene, but it doesn't include any sort of AI stuff like completing the scene or making human talks and so on. There's also conditional 3D synthesis that tries to fill in the missing regions given some partial observations. or you could even do unconditional generation that randomly synthesizes realistic 3D data. So in this talk, I'm going to cover all of these three topics, which is going to be about understanding physics and coming up with a representation for applying deep learning in 3D, and how to apply this technique for doing 3D content synthesis. And I'm going to start from my past work, seeing the world in a bag of chips, that reconstructs the scene and the environment, mainly with physical reasoning. So this video of a shiny bag of chips contains specular highlights, as you can see, the shiny regions. And this specular highlights theoretically contains a lot of information about the environment. But this information is not really interpretable with our naked human eyes. Using a combination of physics and deep learning, we were able to reconstruct a detailed information that could be revealed, such as the general room layout, windows, or even the trees outside the windows. And our result closely matches the ground truth environment, as you can see here. I'm going to give you a brief overview of our method. So the input to our algorithm is an RGBD video. And output, as you just saw, is the environment lighting and the appearance model of the scene, where you can synthesize the novel view of the scene that are not captured from the video. So from this RGBD video, we start by estimating the camera pose using the off-the-shelf SLAM libraries and reconstruct the geometry using a technique called Kinect fusion. We also estimate the diffuse texture using an existing work of myself. The basic idea is to model the specular highlights using a concept that we call specular reflectance map. This specular reflectance map maps a reflection direction, shown as this yellow arrow, to an RGB radiance value. So this SRM is essentially the environment map convolved with the material of the surface. And with this SRM, given this example camera viewpoint, you can shoot the ray and compute the reflection direction, and you can look up in the SRM for the radiance value to render the scene. In practice, however, real scenes have spatially varying materials, meaning that there are more than one materials in the scene. And there's also a lot of geometry and camera parameter estimation errors in the process. So instead, we use multiple basis SRMs. So in this scene shown here, we have the diffuse carpet and the shiny cans. And here we can describe the scene specular highlights using two basis SRMs. One is black because it is diffuse and has no specular highlights. And the other one describes the specular highlights of the metal cans. Now the question is, how do you know which SRM to use for which points in the scene? And to model this, we use a 2D CNN that assigns some blending weights to the two basis SRMs. So this CNN takes input as the diffuse rendering and outputs the segmentation weights, where the number of basis SRM is the input of the user. So given this setup, we can solve for the appearance model of the scene by trying to reproduce all of the input video frames as much as possible. So let's go over the rendering process of the specular highlights in more detail. So given a viewpoint, you can render diffuse texture. And for each ray, you can compute the reflection direction. And you can look up the corresponding pixels in the SRMs, and you can linearly blend the radiance values weighted by the weights obtained through the CNN. And this gives you the specular highlights of that viewpoint. So essentially, you can see that as scene lighting. That's the specular highlights viewed from certain viewpoints. So now we have this forward specular model of a certain viewpoint. We can add the diffuse components that we reconstructed before to form the full appearance model of the scene. And this view prediction should closely match the ground truth across all frames. And we can backpropagate the difference between the ground truth and the prediction to optimize the pixels of the environment maps and also the segmentation CNN weights. In practice, there are significant errors in the geometry and texture. So we had to use the robust loss functions, such as the combination of pixel-wise L1, the perceptual, and the adversarial loss, which can be used to backpropagate the signal end-to-end from the rendering pipeline to the entire network and the SRM weights, SRM pixels. So we can apply this to scenes with arbitrary number of materials. Here, you can see that our algorithm was able to recover 3 SRMs, and you can also render the scene from any viewpoints to get the specular components and the diffuse components, which adds up to the final rendering. So here's some results of the recovered SRMs. The left image is the example frame of the input video featuring a glossy cat decoration. You can see on the right that our method recovers the room lighting pretty accurately. And some results here, when there's a lot of specular highlights in the scene, our algorithm can reveal some great amount of information just from the specular highlights, such as this building across the street. And one thing to note is that the choice of loss function plays some important role in this optimization, so that when you only use L1 losses, it results in the signals becoming washed out due to the errors. And if you have the adversarial and the perceptual loss, the reconstruction gets better. So our method works especially well when there are strong lighting in the environment, which you can see in this example, where you can see a person's silhouette that closely matches the ground truth. Compared to the state-of-the-art lighting estimation methods, our methods provides much more detailed reconstruction because we combine the physical and then the neural rendering reasoning in our pipeline. So once we have recovered these SRMs, we can use them for a task called Novelty Synthesis, which is predicting the appearance from an arbitrary viewpoints that are not captured in your training data. So during the previous optimization stage, I showed that we could do this simple addition to model a novel viewpoints. However, you can see that this simple addition does not look very photorealistic because the textures and the highlights are not as sharp as the ground truth. So instead of doing this simple addition of the 2 rendering components, we train a CNN that takes input as these 2 rendering components and outputs a realistic view prediction. You can think of this as some sort of image-to-image translation. The CNN learns to combine the 2 components into novel views. And you can see that the neural rendered images are almost indistinguishable from the ground truth. This video shows some example results of the novelty synthesis. In this example, these concave balls contains interreflections that are often ignored by most other existing works. Because we use many physical models of specular highlights, especially our method is robust at view extrapolation, which is the task of predicting views that are very far from input views. So in this images, the black frosted indicates the input views that are used for training, and the red frosted indicates the test views that are very far from the input views. And most existing neural rendering works do not explicitly model specular highlights with physics, but rather train a network to produce the input images as a whole. So they often fail to extrapolate viewpoints like this. So here's some demonstration. So in this video, you can see that our modeling of specular highlights provides better extrapolation ability than the then state-of-the-arts. And here's another result. Again, our method performs better than the baselines, which I think really shows the power of modeling physics within the deep learning framework. So to summarize, the contributions of this work include a way of getting detailed environment from specular reflections, and a robust novelty synthesis framework using both physics and deep learning. But the big limitation is that the optimization is done per scene, and there was no prior knowledge being applied whatsoever for scene completion, for example. So in the next part of the talk, I'm going to focus on this other part where we try to learn the prior knowledge from data. And this could be useful for various purposes, such as scene completion, or trying to create new content, new synthesis, and so on. And to do this, we need to come up with a new 3D representations. So this is the project. It's called DeepSCF. And as I said, this is about the new geometry representation that's suitable for 3D deep learning. So in 2D computer vision, as you all probably know, we have made some remarkable progress in generative modeling. So some of the methods range from impressive image completion to image translation results. And convolutional neural networks have been the key components that's driving this progress in 2D computer vision. And this convolutional layer operates in a discretized 2D grid of pixels. So perhaps the most natural and most intuitive extension to 3D would be to discretize the voxels instead of pixels, and processing these voxels with 3D convolutional networks. But this direct extension does not scale very well in space and time. As you can see in these images, that some of them, using these voxels to generate 3D data produces pretty blobby and low resolution results. And even using the octree-based representation gives a blocky modeling of shapes. So these challenges have limited the quality and fidelity of deep learning approaches in generating 3D data. So instead of modeling the scene using voxels, we take a fundamentally different approach, which is to describe the 3D surface as a decision boundary of a neural network. So the key idea here is to directly regress the sign distance function with a fully connected neural network. Specifically, this network takes an XYZ coordinate and outputs a sign distance function of that position. Sign distance function is defined as a volumetric field whose magnitude represents the distance to the closest surface. And the sign of this sign distance function represents whether this point is inside or outside of a watertight surface. And thus, the surface is implicitly represented as the zero level set of the sign distance field, which corresponds to the decision boundary of a neural network that is trained to perform a binary classification task. This signed distance field is widely used in 3D computer vision, but most of them use a discretized voxel grid of stored SDF values instead of using continuous signed distance field. So we can directly regress the continuous signed distance field with a neural network by training it on the point samples of a shape signed distance function. And using the universal approximation theorem, which states that a fully connected network can describe an arbitrarily complex decision boundary given enough weights, it can be theoretically shown that we should be able to represent an arbitrarily complex 3D surface given enough weights in the neural network. And once the network learns this implicit surface, this can be converted into explicit surface through the following two ways. First, we can extract a mesh from the implicit representation by conducting the marching cube algorithm. Or we can shoot rays along the camera direction like this until it meets the zero crossing, and it renders a depth map from a particular viewpoint. Another nice property of this deep SDF representation is that the surface normal can be analytically computed by taking the gradient of the signed distance field with respect to the XYZ coordinate of the surface points. This could be done easily through the standard backpropagation of the neural network. And this analytically differentiable nature of our representation has inspired various papers to adopt a similar strategy to their differentiable rendering pipeline. So far, we explained a case where a network can represent a single shape through optimization. But as I said, this is not very interesting because essentially we want to learn from data and a lot of data and to generalize when given a new scene. So we show that here, we can actually represent a data set of shapes in a single neural network by conditioning the query point with a latent code. So with this formulation, the input to the network will be the code concatenated with an XYZ coordinate, and the network, given those inputs, will output a signed distance function corresponding to those codes and XYZ positions. So now the question is, how do we actually learn this latent space of the data set of a signed distance functions? The most popular way of doing this is perhaps using an autoencoder with an encoder and decoder architecture shown here. However, it is not very clear for us how to design an encoder to process a continuous signed distance function. So instead, we use an alternative architecture that only has this decoder part of the network, which we named as autodecoder. So in autodecoder, the latent code is obtained through an optimization as opposed to the feed-forward pass, and both during training and the inference, we do that. So in deep SDF, the inference and training of the network is equal to optimizing for the latent code in order to minimize the L1 difference between the predicted and the ground truth SDF. There are several benefits of using this optimization during the inference time. The first is that we can use arbitrary number of points for the optimization. So we can have a partial shape for inference or any partial shape. Second is that we have more control of inference compared to the feed-forward pass. For example, we can actually get the optimal code for the reconstruction, or we can add some priors, which I'm going to explain later. So during the training of deep SDF, we first initialize one random code for each object in the scene. And we can then jointly optimize for all the latent vectors in the dataset, along with the weights of the shared decoder network using the standard backpropagation and adding an optimizer. So in terms of equation, we can minimize the difference between the ground truth and the predicted SDF for all shapes in the dataset. And the tunable parameter here are the latent codes Z's for each of the objects and the shared network weight. And as I said before, we can add priors on the distribution of the latent codes. A popular one is being a Gaussian, shown here. So now after this training, we have a meaningful latent space of shapes, which we can verify this by showing some interpolation in the latent space. So this video shows exactly that, shows the latent space interpolation between a pair of training codes. And here I want to emphasize that the size of this neural network trained on thousands of shapes is only about 7 megabytes, which is only about 1/100th of the existing network that are trained to process voxels. So during the inference time, after you train this network, and as I mentioned earlier, we can optimize for the code while keeping this network weights fixed. So we can find a code that best explains the full 3D shape as shown here, or we can perform inference also on partial observations, such as a depth map shown here, because the autodecoder formulation allows you to do inference on arbitrary number of point observations. In this video, we show the visualization of optimization process, which is trying to find a code that best explains the green dots in the middle frame. You see in the right side, the shape is being optimized to fit the backside of the chair. And as mentioned earlier, in terms of equation, we can optimize for the code Z by minimizing the loss in the output SDFs. And a nice property of this autodecoder inference is that we can also add priors in this optimization, which is a difference between this and the feedforward networks. So for example, we can add a distribution prior to the optimization, shown here is a Gaussian prior, or we can ensure that the SDF and the surface normals are physically correct by adding the proper regularization terms shown in the bottom two rows. So our method produces shape reconstruction with much higher quality compared to existing methods such as octree-based representations, and also provides analytical surface normals. And we can do this while having 100 times smaller network size. And we can also do auto-encoding by doing optimization. You can see that the result is better than the mesh-based representations. For shape completion, given a single depth map, DeepSDF completes the back side of the shapes. And compared to the ground truth, you can see that our prediction is more accurate and realistic compared to the voxel-based methods. So to sum up, DeepSDF is an effective novel 3D representation for generating 3D data that introduces the continuous implicit surface representation. And we also propose a probabilistic learning method called autodecoder for training 3D data without an encoder. The limitation of this work is that it's limited to object scale. And currently, the DeepSDF didn't model appearance, just only model the geometry. Now, I want to point out that there has been many exciting applications of this neural implicit representation. For example, it was used for reconstructing humans, used for self-driving applications, robotics, and recently I saw a paper that used implicit representation to reconstruct a black hole. And perhaps most notably, there was a work called NERF, which was introduced in 2020. It has been a really impactful paper. This NERF uses the same coordinate-based representation as used in DeepSCF, the same architecture, but instead of outputting sign distance field as in DeepSCF, NERF chose to output the RGB and opacity value to model the geometry and the appearance of a scene. And using this representation and an optimization using a technique called volume rendering, it can be used to reconstruct a scene given multi-view images very reliably. So far, I talked about DeepSCF and some extensions of these works, using neural implicit representations. But these works mostly rely on 3D supervision. So DeepSCF, for example, relied on the ground truth 3D data from ShapeNet, or NERF relied on multi-view data, meaning that you need to take multiple snapshots of a scene from different perspectives. However, these 3D or multi-view data are relatively difficult to acquire. And the number of data points that already exist in the world for these 3D and multi-view data are relatively sparse and small. On the other hand, there are a lot of 2D image data sets, and you can find them abundantly on the internet. So some of these data sets range from 100K images to close to 1 million data set images with very diverse content and viewpoints, which are hard to obtain in 3D. So now the question is, can we somehow learn a 3D generative models as we did in DeepSCF or other people do in NERFs from these single view images only without 3D supervision? So in the last part of the talk, I will discuss how to use the prior representations in the physical knowledge that are accumulated to use it for 3D content synthesis, and specifically leveraging the neural implicit representation I introduced to learn a synthesis 3D model only from 2D images. So training a 3D generative model from single view images seemed almost like an impossible task, because think about the traditional 3D learning or 3D reconstruction, they try to optimize the pixel-wise reconstruction losses from multi-view data. And because we cannot use the pixel-wise reconstruction losses, we instead look into this idea of generative adversarial networks, where the generator is trained to generate realistic images, and discriminator try to find out whether the image that it got is fake or real. And in this GAN framework, the generator tries to generate realistic images inch by inch by trying to fool the discriminator. And this is a good target because this GAN framework doesn't use any pixel-wise reconstruction losses and doesn't need any correspondences in the multi-view data. So the existing 2D image synthesis techniques, like the scans, has been shown to achieve remarkable photorealism. But the 2D GANs, they do not model the 3D geometry, lack understanding about the 3D world. And thus, they cannot be easily controlled to generate new poses or new camera angles, and will show artifacts and inconsistent behaviors in 3D. On the other hand, as I introduced, there are lines of work on implicit neural representation, including DeepSCF or these NERFs. And they use this coordinate-based representations. The problem of these approaches, even though they produce a really nice overfitting result in a single scenes, they need multi-view supervision. so it cannot be trained with single view images. And on top of that, these networks do not generalize to a new scene. So a different model is required for each scene. So in order to train 3D GAN, we need to combine these 2D GAN approaches and these 3D nerves by rendering a randomly sampled viewpoints given a latent vector. And we use a 2D discriminator to guide the rendered image to look realistic. So in short, these 3D GANs can be trained to generate realistic images for all randomly sampled viewpoints, and thus can be trained without the multiple supervisions. Well, there exists previous works, attempts to combine these nerves and 2D GANs, but they fell short for several reasons. First, their use of inefficient volume rendering leads to limited output resolution. And secondly, their use of this density-based geometry modeling, which means that they don't explicitly model the geometry, leads to an inconsistency on the viewpoints. As you can see on the right side, it changes the identity by the viewpoints. So you could see that it's not really 3D consistent. And you can see here that because the opacity-based representation does not explicitly model the geometry that you can see in the middle column is not perfect and have a lot of artifacts. In contrast, as you can see in this video, our method is able to generate consistent and high resolution RGB and depth images sampled from the 3D GAN. And as I noted, this 3D GAN is only trained from a data set of images. The key idea are the following. So first, we represent the geometry with sign distance function, as I used in DeepSCF, instead of the volume density, which are the common way of modeling geometry by the works and variants of nerves. This enables us to learn the well-defined 3D geometry and significantly improves the view consistency of the rendered images and the depth maps. And then another key idea is we combine the low resolution volume renderer with a style GAN generator. And we first use a 3D scene representation to do the neural volume rendering. And then we upsample it using a style GAN network to render a high resolution image from a particular viewpoint. And as a comparison, you can see that our method produces much nicer 3D consistent images and also consistent and nice depth maps that you can see on the right side. So here's some brief overview. So we take the latent vectors and the view direction positions and render the 2D feature maps, and which can be upsampled by the style generators. And we have a discriminator to discriminate each of these outputs. And this, our backbone architecture is modeled with sign distance function and also the appearance and the feature maps, which can be used to render the 3D scenes from multiple viewpoints. So here are some results of the generated images and the depth maps for the FFHQ and the animal faces dataset. And here are some video results. You can see we can control the viewpoints that you cannot do that for any 2D GANs. And these 3D appearance and the sign distance function models were, as I said, obtained only from 2D images, which is improvements from DeepSCF, which required explicit 3D data ground truth. And here is another example on the animal dataset. So given these 3D GAN, we can come up with some exciting 3D media applications. So when given a input image, like shown in the left here, we can optimize in the 3D GAN latent space to best explains the input image, which is very similar to what I introduced in DeepSCF with the autodecoder architecture. So our 3D GAN then automatically models the geometry and the appearance of the image in 3D. Note that this particular demo is not from myself, but from the work that I'm not part of, which take our pre-trained 3D GAN model for these third tasks. And doing this optimization and finding in the latent space allows us to not only rotate the image because we have the underlying 3D structure and view this person from different perspective, but also the existence of the underlying geometry really allows us to solve for the lighting and the materials that were not possible if you just have the images. So this allows us to enable the change of the viewpoints and the relighting of the scene as well. And here's another example where, given an image, we can use our pre-trained 3D GAN model to enable novelty synthesis and some expression changes. Okay, now that you've seen the 3D GAN work, you might wonder, can we model more? Can we model even 4D? Because we live in the 4D world. Spatial temporal data generation is going to be very useful. For example, if you want to model human motions, or you want to use training data for robotics or self-driving, etc., this would be very useful. So the question is, can we train a 4D GAN from unstructured videos with similar technique that I use in 3D GANs? So in this work, which I recently submitted, we demonstrated that the training of first 4D GAN. The following three changes we made from the 3D GANs. First, instead of using the image dataset, we use video dataset, obviously. And second, we use input as XYZ-T coordinate, as opposed to the XYZ coordinate to the implicit neural network. And we condition the network with two latent vectors instead of one, one being the content latent vector, and the other one explains the motion. The last change we made is from the discriminator, which needs to learn realistic movements as opposed to just learning the realistic appearance. So this discriminator takes 2 frames instead of 1 frame and is conditioned on its time differences between the 2 frames. So with these 3 changes, we're able to learn a 4D GAN model, which is able to sample a random 3D content that has movements in it. And because it's 4D GAN, we can you can rotate it around, for example, and see the faces from various camera viewpoints and the various time steps. And a nice property of our framework is that we can get the motion and the content decomposition for free because we model the 4D field with two disentangled latent vectors. And we can apply the different motion vectors to the same identity, same here, shown here, or we can apply the same motion vectors to different identities, shown in the bottom row. And we also tried applying our method on non-phase datasets, like this video dataset of people doing Tai Chi. Or we also tried to reconstruct the sky time-lapse video dataset. The quality isn't as high as the dataset for the faces, but it shows a new exciting direction for and possibility for 4D GANs. And because these skies are modeled in 3D, you can similarly rotate it around in different axes. So today, I talked about my past works towards realistic synthesis of 3D content. And as I mentioned earlier, to achieve this task, I discussed how we can model physics of light reflection to reconstruct environment map and also the scene appearance. Also, I introduced a new way of representing 3D data that is suitable for deep learning and synthesis compared to existing representations. And finally, I talked about how to use this coordinate-based neural implicit representations to train 3D and 4D generative models. There are many exciting future directions that I want to pursue, and I believe other persons should be excited about too. One area is to model large-scale compositional scenes. And I want to go beyond purely statistical reasoning to train statistical models, but also reason about physical and semantic interactions between entities in the scene, which has not been explored properly in the literature. Another interesting direction is to enable virtual interaction with the reconstructed or synthesized scenes, such as picking up some stuff, the fruits in the scene, sitting on sofa, or etc. I think these are very important problems that we haven't solved, which could be useful for robotics or augmented reality tasks. Another interesting area of research would be to synthesize 3D content with a conditional generator, such as a model that's conditioned on language inputs. So before I finish my talk, I would like you to think about how much our lives have changed because of the 2D media. With the development of 2D media, photos and videos have become the main source of our personal memory. And they changed how we communicate and how we share our experiences with friends and family. 2D media has also changed how we consume new information, and it even changed how we eat. So it would be very interesting to imagine how much change will the new 3D media will bring to our lives in the next couple of decades. And it could be similarly dramatic. It could bring changes how we perceive the world, how we consume information, communicate with others, or travel to new places, and so on. It also brings a lot of changes of our domestic lives with, assisting robots, and it also changed transportations and could revolutionize how things are manufactured and transported. So I'm very excited to witness and be part of these changes in the 3D media and the changes that it will bring in the next decades. Thank you very much for listening, and please let me know if you have any questions.